Now we'll do an example of trying to figure out the force exerted on a smooth plate that is immersed in water flowing at 4 meters per second. So plate is, edge on. So from the side view, flow is, coming at the edge, going to flow over the top and the bottom of this plate, and it's going to exert a force on the plate through the viscous effects. So first of all, in order to do this, we need to know whether we're dealing with a laminar or a turbulent flow. And to do that, we need the Reynolds number. So we would need the Reynolds number anyway, but we might as well get the Reynolds number for right away for pretty much any problem of this type. So let's get Reynolds number. We know that the nu of water is equal to 1 times 10 to the minus 6 meters squared per second. And that is all I need to finish up the Reynolds number. I have all the other dimensions. The Reynolds number is equal to, of course, U infinity, which is 4 meters per second, times the length of the plate, L here, so 0.6 meters, divided by 1 times 10 to the minus 6 meters squared per second. So calculate that out, and we get 2.4 times 10 to the 6th. No units, of course, because it's a dimensionless parameter. So there's our Reynolds number. So that's solidly turbulent, so we're definitely in the turbulent regime. And the question is now whether we can consider this to be, almost all turbulent, in which case we have one relationship we use, or whether it's, got some laminar and then some turbulent. So the question we're asking is, is the transition Reynolds number X point, is that a lot less than L, or is that transition point, not so much less than L, that we really need to consider both the laminar and the turbulent regimes. So in order to calculate that, we actually have that criteria already. The relationship that I was given, we were given, said there was one relationship we used for Reynolds numbers less than 10 to the minus 7th. So that is the relationship we're going to use. We have Reynolds number of 2.4 times 10 to the 6th. So we're going to use the Reynolds number less than 10 to the 7th relationship, and that's the one that's for a mix of both laminar, a small laminar regime, and then a turbulent regime, but not a laminar regime that's so small that we can simply ignore it. So the relationship that we use then is that one for less than 10 to the minus 7th, which is that the skin friction coefficient average is equal to 0.073 Reynolds number based on L to the minus 1/5 minus 1700 Reynolds number based on L to the negative 1. And as I said, this is good if your Reynolds number is less than 10 to the 7th, but the flow is turbulent. And that's exactly where we are. 2.4 times 10 to the 6th, less than 10 to the 7th, but above the transition of 5 times 10 to the 5th. So that's our relationship. I'm going to plug some numbers in here. I have the Reynolds number, so I'm basically done. CF bar is equal to 0.073 times 2.4 times 10 to the 6th to the minus 1/5 power minus 1700 divided by 2.4 times 10 to the 6th. Well, pretty easy. Solve that for CF. Plug in that into my calculator. I get 3.87 times 10 to the minus 3 minus 7.08 times 10 to the minus 4. And finally, obviously, I can just subtract those, and I get 3.16 times 10 to the minus 3. So that's my final answer for the skin friction coefficient, average skin friction coefficient. Again, no units here because skin friction coefficient is a dimensionless parameter. So that's nice. We don't have to worry about units until we start plugging in numbers. Now we say, okay, we have to remember the definition for the skin friction coefficient. That's the average wall shear stress times 1/2 rho v squared. And so we can easily calculate the wall shear stress from that. The average wall shear stress is equal to, obviously, 1/2 rho v squared times the skin friction coefficient, which we just looked up. So that's equal to 1/2 rho v squared times that thing we just calculated, 3.13 times 10 to the minus 3. And that gives me, when I plug in rho and v squared, 4 meters per second, rho of water is 1,000 kilograms per meter cubed. I get that the average skin friction coefficient is 25.3 newtons per meter squared. So that's my average shear stress exerted by the fluid on the wall. And now I can just get a force by multiplying 2 times 25.3 newtons per meter squared times the area. And the 2, of course, is because we have 2 sides to that plate. We have the top and the bottom. They're both experiencing equal stress. And the area of the plate is simply the width times the depth, width times the length. So I have that F is equal to 2 times 25.3 newtons per meter squared times 0.6 meters times 1.2 meters. And so finally I get F is equal to 36.4 newtons. So the total force exerted by that water on that plate immersed in flow that's traveling at 4 meters per second is 36.4 newtons.